alcohol is a molecule that has an OH attached to a carbon chain. If the carbon that is bonded to the oxygen is bonded to just one other carbon, it's described as a primary alcohol. If the carbon that's bonded to the oxygen is bonded to two other carbons, it would be described as a secondary alcohol. So this here, what's drawn here, which is ethanol or drinking alcohol, that is a primary alcohol. If you have a primary or a secondary alcohol, you can replace the OH with a Cl. You can turn the primary or secondary alcohol into a primary or secondary alkyl chloride by adding these reagents here. The reagent on the left, SOCl2, is called thionyl chloride. The Py on the right is standing for a molecule called pyridine. Thionyl chloride is a clear liquid. It can sometimes have a slightly yellow tinge, as you see on the left here. Pyridine is a clear liquid, as you can see on the right. In the first step, the oxygen of the alcohol has a slightly negative charge. Oxygen is really electronegative, so it pulls electrons to itself from the carbon and the hydrogen that it's bonded to, and so it becomes slightly negative. It acts as a nucleophile. It attacks the sulfur on thionyl chloride. You can see the structure of thionyl chloride here. The sulfur is bonded to two chlorines and then double bonded to oxygen. So the sulfur is bonded to a lot of electronegative elements. The chlorines pull electrons to themselves. The oxygen pulls electrons to itself. All of these are slightly negative. The sulfur is really slightly positive. So it acts as a pretty good electrophile, and that's what convinces or persuades this oxygen to attack it. When the oxygen attacks, the weakest bond, which is the pi bond here, breaks. Remember, the first bond you ever form between two atoms is a sigma bond. Every bond after that is a pi bond. So as this oxygen attacks, the weakest bond, this pi bond, breaks, and the electrons go onto the most electronegative place nearby. That's this oxygen. So this is nucleophilic attack, adding the oxygen onto the sulfur. After that step, this molecule has two charges. The oxygen now has three bonds. Anytime oxygen has three bonds, it has a full positive charge. The other oxygen down here only has one bond. The electrons that were in the pi bond have gone fully onto this oxygen. Anytime oxygen only has one bond, it has a full negative charge. So these are sort of fires that are broken out on the molecule that we have to put out. We put out this positive charge fire by adding the base pyridine, and this is abbreviated as a Py in the reaction. Pyridine is a six-membered ring where one of the atoms is nitrogen, and the bonds are alternating double, single, double, single, double, single bonds. The lone pair on the nitrogen can act as a base and accept H pluses. So the pyridine is really here to do a proton transfer, to rip an H plus off of the molecule. The electrons holding onto that hydrogen will snap back to the most electronegative place nearby, this oxygen, and put out that positive charge. So after you do that proton transfer, that oxygen is now stable. We still have the other charge on the oxygen, though, this negative charge at the bottom here. That's still unstable. This oxygen here. If you look at the sulfur is bonded to an oxygen, two chlorines, and another oxygen. All of those are very electronegative elements, so they're all pulling electrons away from the sulfur. So the sulfur is losing a lot of electron density and becomes really slightly positive. That's very attractive to the electrons on this negative oxygen. So one of the lone pairs on that fully negative oxygen getting repelled by the others goes to form a bond toward the slightly positive sulfur. But if you're going to form a new bond, one of the bonds that's there has to break, and one of the chlorines, which is a good leaving group, takes the electrons holding it to the sulfur and leaves. So this is a loss of a leaving group. So you reform the pi bond and one of the chlorines leaves. At this point, the molecule is now stable, and the chlorine that left has a full negative charge. And the stage is set to do an SN2 reaction. We've attached this SOCl where the H was, And this whole group is now a good leaving group. So it can leave, it can take these electrons and leave, and they'll be stabilized on this oxygen through resonance because they'll be allylic to this pi bond. The chlorine has a full negative charge and so can act as a nucleophile. So this carbon here that's bonded to the oxygen's pulling electrons away from it, the carbon is slightly positive. So this chlorine can swoop in, attack that carbon, that's our nucleophilic attack that's going to add the chlorine. And the electrons holding onto this large weird group can snap onto the oxygen, and the leaving group can leave. That's loss of a leaving group. Notice, this is an SN2 reaction. Anytime you have nucleophilic attack and loss of a leaving group happening at the same time, it's an SN2 reaction. So when that SN2 reaction happens, the chlorine is attached to this carbon, and this other group has left. Notice the lone pair on this oxygen that has a full negative charge is allylic. It's one atom away from this atom involved in a pi bond, and so it can spread out through resonance. So, as a bird's eye view, that mechanism shows you how you can start with a primary or secondary alcohol, and using thionyl chloride, which is SOCl2, and pyridine together, you can replace the OH, the alcohol, with a chlorine and make an alkyl chloride. So this is the mechanism for an SN2 conversion of a primary or secondary alcohol into an alkyl chloride.